All right, so our last chapter of Chem 1B. I know everybody's real sad to see it conclude here. Nuclear chemistry. All right, so let's start with the obvious question. What the heck is nuclear chemistry? Okay, so most chemical reactions, actually every single chemical reaction that we've studied up until this point, are about making and breaking bonds, right? So most chemical reactions make and break bonds. And what are bonds made out of? Electrons, right? So in chemistry and chemical reactions, most chemical reactions are really just about shuffling electrons around, changing which atoms are bound to who, right? So by making and breaking bonds, bonds are made of electrons. All right, so that's the interesting bit about chemistry. That's most chemistry, is really just about making and breaking bonds which are made of electrons. However, there is this small subset of chemical reactions that occur within the nucleus of an atom. Okay? And chemical reactions that occur in an atom's nucleus are what we call nuclear reactions. And which two subatomic particles are living in the nucleus of an atom? The protons and the neutrons, right? Up until now, those have just kind of been balls, this dense ball sitting in the center of our atoms. They haven't actually participated in the chemistry other than, providing some positive charge from those protons. This chapter will all be about the chemistry of those protons and neutrons. Okay, so we got some terminology to learn here. Let's zoom in on the nucleus of an atom. The subatomic particles that live in the nucleus of an atom, again, protons and neutrons, are what we call nucleons. So our two nucleons are protons and neutrons. Okay? And again, protons have a charge of +1 charge, and neutrons have a charge of 0. All right, so this brings up like this very weird question here, which is we have this nucleus, this very small, dense ball in the center of our atom. And it's consisted of positively charged protons and neutral neutrons. But of course, positive charges, what? Attract or repel one another? Repel one another. So how the hell do you cram all these things into that dense ball in the center of your atom, right? Why aren't these nuclei just like exploding out? Why are they stably held together? And that's because of this force that we have not talked about, which the physicists really broke the bank in creativity here. This is what is called the strong force. The strong force is this very specific type of force that holds nucleons together. So nucleons have this attractive property to one another where they are held together through what is called the strong force. So this is attractive force between nucleons. Okay? And if you go on to like advanced particle physics, you'll dive into this strong force a little bit more. The bottom line is that strong force, that force of interaction between the nucleons, is actually stronger than that electrostatic repulsion between those protons. Okay? Strong force will only take place at very close distances. So if we have two protons and they're separated in space, those electrostatic forces are dominant. They're repelling one another. They hate each other, repelling, and all of a sudden they get close enough and they're like, all right, fine, I'll bond with you. Okay? That strong force takes over at very close distances. It's just this very special interaction that exists only between nucleons. Okay? So again, at very small distances, that strong force dominates that electrostatic repulsion, which is why our nuclei aren't just constantly flying apart. Right? So only at very close distances, our strong force beats that electrostatic repulsion. All right, and so again, if you go on to like more advanced particle physics, you'll learn about quarks and all this other crap that's happening in there that frankly I know nothing about. All right, never got into particle physics. All right, so we got to learn some symbols here. Symbols. There's an M in there. For what are called nuclides, and these are specific isotopes. Okay. So we got some symbology to learn here, specific to nuclear chemistry. All right, so for example, C represents which element? Carbon. Great. If I'm going to talk about a specific isotope of carbon, I can talk about, for example, a carbon-12 atom. Okay? This is what we would call carbon-12. So this number that's in the lower left-hand corner here, this is just the atomic number. And it's actually not uncommon to just omit that altogether because it's kind of redundant, right? By virtue of saying it's carbon, you know that it's atomic number 6. Okay? Our book does keep track of it, and so we're going to keep that there. This number here is what's called the mass number. All right, and the mass number describes a specific isotope because your mass number is equal to the number of protons plus the number of neutrons in your atom. So we got to do a little bit of math to figure out how many neutrons we have here, but how many neutrons are there in a carbon-12 atom? 6, right? My atomic number, my number of protons is 6, and so that leaves 6 plus 6 would give me 12. Just to be clear, hopefully we all know, but atomic number is the same as number of protons, right? That's what our atomic number is telling us. Okay? So then take a second and see if you can't draw me the symbol for a carbon-13 atom here. Okay? So again, my symbol's carbon. My atomic number is 6. But notice that in my name here, that dash whatever number, that's your mass number. So this would be a carbon-13 atom here. That would be my symbol. So that a carbon-13 atom has how many neutrons? 7, right? Different than a carbon-12. This is what we would call a pair of isotopes. Isotopes. Same element, i.e. same number of protons, but a different number of neutrons. It's one fancy N. All right, so many of our elements, they actually exist in more than one isotope. So carbon, for example, all the carbon in the universe is carbon-12 or carbon-13. Okay, so there is, it turns out that carbon-12 is the more abundant of the two. The vast majority of carbon in the universe is carbon-12, but there is a small amount of carbon that actually contains 7 neutrons instead of 6. Both of those are still carbon atoms, right? They still got those same 6 protons. That's what makes carbon carbon, but they have a different number of neutrons. All right, and again, this information is summarized in our little symbol here. All right, each one of these individually are what are called a nuclide. All right, so a pair of nuclides is our isotopes. Okay, so these symbols are going to be really important because, again, the chemistry that we're talking about in this chapter happens at the nucleus. All right, so for example, if we take a uranium atom, specific nuclide of uranium, uranium-238, uranium has 92 protons. What do we know about uranium? What is it used for? Nuclear power plants, or maybe more evilly, nuclear bombs, all right? So these nuclear reactions, uranium is very central to those. And what happens in these reactions is the uranium atom, just that atom all by itself, is going to fall apart into 2 smaller components. Okay? One of those would be a helium-4 atom. All right? And I want you to try to tell me what the other one would be here. All right, so everybody take a second and copy this down. And then we're going to have to go to our periodic table here. All right, ignore all this. Right, so I'm trying to figure out what this other component is. All right, so when we're balancing these nuclear reactions, there is this very simple principle that we're going to apply here, and that is this idea of conservation of matter. Protons can't be created or destroyed. Neutrons can't be created or destroyed, right? So that means that the number of protons on my reactant side has to equal the number of protons on my product side. And the number of neutrons on my reactant side has to equal the number of neutrons on my product side. Right? I can't be creating or destroying these atoms or these subatomic particles out of nowhere. So that's the principle that we're going to apply to balancing these nuclear equations. If uranium has 92 protons, and it breaks up into helium that has 2 protons, what's the other fragment going to have? How many protons? 90, right? Because I got to have the same number on both sides. So as soon as I do that, I can go ahead and look up element 90, which is, these are all going to be bizarre sounding ones, right? The ones that we're less familiar with. Thorium, actually pretty badass sounding name, all right? But nonetheless, so TH. And then what's going to be the mass number of that thorium atom that's formed? I got my 238 here, but I have to have this conservation of my subatomic particles. So if my mass number of helium's 4, my mass number of my thorium has to be 234. They got to sum to that same value. 4 plus 234 gives me my 238. Just like 2 plus 90 gives me my 92. All right, so we have this conservation of matter. I guess actually we need our periodic table. So let's just do another one here. All right, another one that you will often hear about being involved in nuclear reactions is plutonium. If plutonium breaks up into a cobalt 60, tell me what my other fragment must be here. What's the atomic number of my other fragment going to have to be? 67. So then I'll go look up element 67, holmium. Again, who's heard of that? And then what's the mass number of my next fragment going to be? The 184. All right, so balancing these nuclear equations, we have this very simple principle, right? We just have to have a conservation of matter. The number of protons on one side has to be the same as the number of protons on the other side. Number of neutrons on one side has to be the same as the number of neutrons on the other side. Okay? All right, so now we're going to learn about different categories of these nuclear reactions. Oh, not there yet. All right, so our first type of nuclear reaction is what's called alpha decay. Let's take, for example, we actually sort of saw an example of this. This would be our uranium-238 example. Okay, where it breaks into that helium-4 and that thorium-234. All right, so some terminology here. The thing that you start with that ends up falling apart, this is what's called the parent nuclide. The other big chunk is what's called the daughter. And that helium particle is what's called our alpha particle. So alpha decay is a nuclear reaction that necessarily produces an alpha particle, that helium 4 component. All right, that's what makes alpha decay alpha decay. And why would helium be a common sort of component of these reactions? What do we know about helium? Where does it live on the periodic table? It's a noble gas, right? Something that's nice and stable, a teeny tiny noble gas, right? So helium is a very common product in these nuclear reactions. And if helium is a product, that's what we call an alpha decay. Another type of nuclear reaction, they really just run through the Greek alphabet here. Beta decay. All right. So if, for example, we have a carbon-14 atom, nuclide, this would decompose into nitrogen 14, and eject an electron here. So the signature of these beta, so I guess first of all, this is what we call the parent. The nitrogen here would be the daughter. And the electron is my beta particle. What's very special about these reactions is I didn't just take a carbon atom and flick off one of the electrons, right? That would just create a carbon ion. I have a proton that's actually been converted into an electron here. So notice that my mass number stays the same. But the number of protons goes up. All right, so notice that we're increasing our atomic number in these beta decays. Our next category, again, going down the Greek alphabet, is what's called gamma ray emission. I think I misspoke. It's not an electron that gets converted to a proton. It's a neutron that gets converted to a proton. That's why my mass number stays the same, but the number of protons goes up. I misspoke, my bad. So beta decay, we can just say explicitly, neutron converted to proton. That's why my mass number doesn't change, but my atomic number goes up. I apologize. And in that process, an electron is being ejected. A beta particle is being ejected. All right, so gamma ray emission is where what's called a gamma ray. A gamma ray is like a super high energy photon. All right, so remember, photons, that's what light's made out of. What we're seeing right now, what's being captured by our eye are photons, but within a certain region of that electromagnetic spectrum that we call visible light. We got even higher energy photons that we take advantage of when we do X-rays, for example. Gamma rays are even higher energy than that, the highest energy photons that can be produced here. So a gamma ray is a high energy photon. Not something you want to be in the way of. All right, very, very bad for you, can penetrate easily and way too high energy. This accompanies other nuclear reactions. So these alpha and beta decays that we've talked about before, quite often they're also paired with a gamma ray emission. Right? What do we know about nuclear reactions? Do we want to be chilling next to one when it happens? No, that's because they produce ridiculous amounts of energy, something that we as a human race have taken advantage of in creating nuclear power plants. All right, but that ridiculous amount of energy that is released is in the form of heat, but also in the form of these very damaging gamma rays here. So let's take a look at an example. Say that we have a rhodium that first undergoes alpha decay, and I want you to take a second and tell me what my products would be if I'm telling you it undergoes alpha decay. So if I'm telling you it's alpha decay, you absolutely for certain know that one of those products is what? That helium, right? Specifically that helium-4. And the other one is going to have an atomic number of 43 and a mass number of 99. If we look on our periodic table, element 43 is technetium. Okay? But it turns out that in this one here, our new bit here is that the technetium produced is going to be 99M. All right, so what the heck does that mean? If you see this, it means that that technetium produced is what's called metastable. All right, which really just means that that technetium 99 is immediately going to undergo gamma ray emission. Okay, this is our symbol for a gamma ray. It's a photon. It's got no mass. It's got no charge. It's essentially just a ball of energy. Okay, so if something appears with that symbol M, it means it's metastable and will immediately undergo gamma ray emission. Okay, so these three, what's up?
Do we write the gamma ray emission part, or do we just leave it as that?
No. So you wouldn't necessarily know, if I just told you that this was alpha decay, you would not necessarily know that there was something metastable produced. But if you were told that there was something metastable produced, you would be expected to be able to draw our gamma ray emission equation. Okay? The point being is that these don't just happen randomly by themselves. They're always accompanying other forms of nuclear chemistry, right? So they'd be on the back end of an alpha decay or the back end of a beta decay, something like that. All right, these three, by far the most common. So there's two properties of these three types of reactions that we're going to talk about. The first one is what's called ionizing power. Okay? And this is the energy of that ejected particle. Okay? So, an alpha particle, really just by virtue of having that mass accompanying it, right? Huge amount of mass in that helium particle compared to, say, a gamma ray. It has the greatest ionizing power, then a beta particle, and then a gamma particle. Don't get me wrong, all three of these have a large amount of energy, but if we're going to rank them, the alpha particle has the highest ionizing power, then the beta, then the gamma. The other thing that's very important, especially if you're considering safety of nuclear reactions, are what's called the penetrating power. All right, and this is just the ability of the ejected particle to penetrate certain materials. All right, so which one do we think would be the best at, say, penetrating your hand? The gamma, right? So then it's the exact opposite consideration. The smallest one has the greatest penetrating power, followed by the beta particle. The alpha particle is just very large, bounce right off, right? The least penetrating power. Okay, what's up?
So can we basically say that the alpha is the biggest size?
It is by 1000% the biggest size. Yeah, like a physical helium atom, right? The gamma ray is literally just a photon made of the same thing as light, just a lot higher energy. If it was coming out of this light bulb right now, you'd be blind. All right, but still just a photon, right? No mass associated with that gamma particle. Electrons are kind of in the middle. They do have a small amount of mass associated with them, but nowhere near as much as 2 protons and 2 neutrons like an alpha particle. All right, and there's 2 more types of nuclear reactions that we're going to learn about that are more rare but nonetheless very cool. All right, the first of which is called positron emission. This is where a proton gets converted into a neutron and a positron. And we will talk about what the heck a positron is here in a second. But let's just look at our nuclear equation and get some freaking room here. All right, so if we have, for example, a phosphorus 30 as our parent, and it decomposes into silicon 30 as the daughter, our other particle here is what's called a positron. So I'm going to tell you, we're going to use this symbol E. And let's just think here. What should the mass number of that positron be? 0, right? My mass number didn't change. And what's the atomic number of that positron? +1, right? In order to have this like conservation here, but this is not a proton. It's what's called a positron. All right? Now, again, this is not a high-energy physics class, and to be honest, I barely understand this crap, all right? But it turns out that for every particle that exists, there is also an antiparticle that exists, okay? So, protons, there are antiprotons. Neutrons, there are antineutrons. And for electrons, their antiparticle is what are called positrons. Okay? So, it turns out that if we take an electron and we take a positron and we combine these two together, remember we said particles can't be created or destroyed. That's kind of a lie. Energy can't be created or destroyed, but we actually can change the form of matter. And how does that happen? By taking a particle and colliding it with an antiparticle. So this doesn't equal nothing, but it just turns into a big ball of energy, again, what we call a gamma ray. Okay? Theoretically, and this is a very sort of theoretical physics sort of thing, something that was not appreciated until like mid-1900s quantum mechanics came around, but for every particle that exists, there's also an antiparticle. In fact, it was thought that at the beginning of the universe, there was about an equal amount of particle and antiparticle of everything, but just a small excess of particles. And over time, all those antiparticles found the particles, and what we're left with here now is just that small excess of particle that existed. Again, cool, great. All right, this is what we got to know here, though. All right, so again, a positron is the antiparticle of an electron. And to be honest, this was a really big win in terms of like computational theoretical physics here. Again, for a long time, the math of quantum mechanics told them about the existence of these antiparticles, and it was studying this type of radiation right here that gave them evidence of that. So it was kind of a big win in terms of the theoretical physicists here. All right, and then the last one is not quite as cool sounding. This is what's called electron capture. Electron capture is when you have a proton combining with an electron to produce a neutron. So if we take, for example, a ruthenium-92 atom, okay, and we add an electron here, right? We're not just nicely placing that electron on in order to create an ion. We're literally doing a reaction between the proton in this molecule and that electron. And again, it's going to turn into a neutron. So what's going to happen to my mass number? It's going to stay the same, right? Because protons plus neutrons. If a proton is converted into a neutron, my mass number doesn't change. But what's going to happen to my atomic number? It's going to go down. All right, so let's just note for our positron emission, our mass number stays the same. But my number of protons goes down. For electron capture, my mass number also stays the same. All right, and my number of protons also goes down. All right, so in terms of the products of your nuclear reaction, both of these have kind of the same effect here. Your mass number is staying constant, but you're decreasing in your atomic number. All right, so now let's take a look at this figure here. I'm going to get rid of this stuff real quick. Okay, so first of all, let's just sort of look at this chart real quick. On the x-axis here is the atomic number, and the atomic number corresponds to the number of what? Number of protons, right? So atomic number, that's just code for number of protons. And on my y-axis here is the number of neutrons. All right? If we zoom in here, this red line is when the number of protons equals the number of neutrons, right? So just your x equals y kind of line on this graph here. If we zoom into our smallest elements here, we see that the number of protons and the number of neutrons in those smaller elements is about on par. Okay? As we increase in our size, though, these larger elements tend to have more neutrons than they do protons. And that's to help counter that electrostatic repulsion force, right? We need more nucleons in there for that strong force to hold everything together. So what are these colors telling us? In yellow here, or I guess we'll do green first. In green are all the known stable nuclides. And in yellow are all the known unstable nuclides. Okay? So, let's zoom in here. Here is a particular, let's just pick, I don't know, what's atomic number 60? Hold on. Great, zirconium, let's do that. So look, everything here, atomic number 40, these are zirconium atoms here. Okay? So we got a few stable zirconium nuclides here. All right, but what if I'm up here? I'm still zirconium. I still have those 40 protons. But now I have too many what? Too many neutrons. Right? So this would be unstable, meaning that it's going to undergo a nuclear reaction until it gets to one of these more stable nuclides. Okay? So, if the number of neutrons divided by the number of protons is too high, that means we have too many neutrons. All right, that means that you're in this region of the curve here. You're above this green line. N over Z is too high. These will undergo beta decay. Because beta decay is converting a neutron into a proton. Right? So mass number stays the same, but you get rid of that neutron by converting it to a proton. If we're below that green line, if our N over Z is too low, then we got too few neutrons. these will undergo either positron emission or electron capture, both of which have the same effect of increasing the atomic number while keeping the mass the same. I'm sorry, decreasing the atomic number while keeping the mass the same. All right, and then last thing we want to note about this chart. There's this magic cutoff to this green line here, right? Notice that all of a sudden, past this point here, there are no more stable nuclides. All right, this magic number here is 83. Elements that are larger than atomic number 83 are just inherently unstable. They will undergo nuclear reactions. All right? So if our atomic number is greater than 83, these are just too friggin' big. And these will undergo a combination of alpha decay and beta decay. So an example being uranium, and again, we take advantage of that by putting uranium in our nuclear reactors. This is not something that you would know just by looking at it, but what scientists have discovered over very many times. What happens with that uranium-238 atom is it undergoes a series of alpha decay, then beta decay, beta, alpha, 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 all the way until it gets to a stable nuclide, which would be, in this case, lead. Right? But it's going to keep on reacting, keep on undergoing these nuclear reactions until it gets to its atomic number that's less than that magic cutoff, 83. So in the 15 seconds that we have left here, just for the sake of completing things here, if I said that a stable isotope, the only stable isotope of fluorine is fluorine 19, then what type of nuclear reaction would fluorine 22 undergo? Yeah. All right, so in this problem, I'm telling you, fluorine 19 is stable, and in fact is the only stable isotope of fluorine. So if we're talking about fluorine 22, does that mean N over Z is too high or too low? Do I have too many neutrons or too few neutrons? Too many. And what type of nuclear reactions happen when N over Z is too high? Beta decay. All right, so this is the type of problem that I would expect you to be able to do with this information. If I tell you what the stable isotope is, and I give you this unstable one, you should be able to determine whether N over Z is too high or too low. And based on that information, tell me what type of nuclear reaction this undergoes. Again, too high implies beta decay. All right, that was a sprint, but congratulations. That is the last bit of new information that we have for our Chem 1B semester here. We're just going to spend next week doing a review. Well, so N is the number of neutrons, and Z is the number of protons.